Hey everybody, thanks for joining the term project poster session where I'm going to be discussing alluvial fan surface roughness from Lidar data in northern Panamint Valley. Alluvial fans record valuable information about sedimentation as well as the style and rates of erosion. When dated, their surfaces represent distinct time markers that can be used for fault rates as well as past climate changes. For this term project, I present a method for using LiDAR data to generate a DEM and extract parameters of surface roughness for a fan in northern Panamint Valley. Panamint Valley is located at the southwest edge of the Basin and Ranges province between the Argus and Panamint Ranges. For the past 4 million years, Panamint Valley has become dominated by right lateral strike-slip motion of the Hunter Mountain Fault Zone, which is marked there by the red star. This region receives a precipitation around 5 centimeters per year, causing sedimentation to depend on episodic debris flows. Fans are distinct depositional landforms common along mountain range fronts where transport energy decreases as the sediment exits narrow canyons. Because incision varies over the active bar and swale topography, multiple generations of fan surfaces are established. This diagram below illustrates the evolution from time 1, showing prominent bars and swales, to time 4, in which convex hill slopes form at the edges of the fan surfaces. Note the larger value for the scale bar in times 3 and 4. So the method I follow is from a study by Kurt Frankel and James Dolan from 2007, in which they differentiated 6 lithostratigraphic units of a fan in northern Death Valley by deriving a slope model from LiDAR data. To start, I used Open Topography to download a last point cloud. The data was originally provided to EarthScope's Plate Boundary Observatory by the National Center for Airborne Laser Mapping, which flew this mission in 2007. The last file contained 9.8 million points with an average point density of 4.61 points per meter squared. I also grabbed a natural color image from USGS's NAPE program for comparison. The first thing I did was create a last dataset in ArcGIS Pro and generate a digital elevation model with 1 meter resolution. I also created a hillshade from that to use for overlays with other rasters. From the DEM, I produced a slope map with raster function tools in ArcPro, and following the methods from the 2007 study, used focal statistics to derive the standard deviation of slope with a 5 by 5 meter moving window. The window size is to account for boulders, vegetation, and the 5 to 10 meter wavelength of bars and swales. In the roughness map created, the smoother surfaces displayed in blue represent older fan surfaces compared to the active channels with higher roughness values displayed in red. And then there's also an example of a 3 by 3 moving window that I grabbed from the 2007 study. So before completing Lab 6, I gave an attempt at classification through the object training functions in ArcGIS Pro to see if I could generate fan units from the standard deviation of slope map. First, heads-up digitization for each channel and surface. And you can see the training samples that I've selected there. I only built a schema with 3 units, creating a very generalized fan stratigraphy map. It seems possible to identify subclasses such as Q2C or Q4A. However, further analysis should be performed for more accurate results. The plots shown here are from a more extensive study that include parameters such as curvature, aspects, as well as varying the moving window size. And that's all I have for you guys. Thanks.